DraftScience video. Continuing with this episode 13, Forces and Fields. Yeah, like I said, I think this is a very good mechanism for revealing the where things go wrong, what premises screw everything up. So I'll just highlight for this segment the understanding of the E equals mc squared thing and the real implication, which is you're kind of made of the stuff still moving the speed of light. So whether you think of it as light, or you think of it as gravity, or you think of it as magnetism, what you're full of is force. Force caught in, bound, however you want to say it, in spirals, in circles, in orbits. It's really positions, but let's just call them orbits for the sake of simplicity. And so they're still moving the speed of light, and so those are essentially the components that you're made out of. And so in understanding interactions in space with other objects, you have to understand that your material velocity doesn't change the velocity of the fish. So when a school of fish moves, because I add more fish moving in the direction, primarily moving in the direction of the school, so the fish that I introduce spend more time going this way than they spend going down and up, or left or right, you know, the other two dimensions. So they spend most of their time going this way, and the minimum amount of time going any other direction. So if we were to use the fish analogy, just to keep them all in the school, right, because we have to turn them around some way. So they spend less time doing the down and around than they spend doing the long. They go this way a lot, they go this way the least amount, and this way the least amount. And so that's velocity of matter. So the fish are going the same speed. So when you interact with something coming at you, technically it's going to be fish against fish. It's not school against school. So when you interact with another force like light coming towards us, the light, no matter how fast I'm going, is still going to be fish against fish. It's not going to be anything different. It can't combine any speeds. My fish are still going the speed of light. The thing coming at me is the speed of light. It'll always be that kind of interaction. Even if I'm standing still or I'm moving, the fish that does the interacting is still going to be going exactly the same speed. And that's what they don't get. Yeah, so they have to come up with a whole bunch of weird crap because they ain't getting that simple thing.
Faraday's big idea, and magnetic fields and forces work out pretty much the same way. It is natural to imagine that the same idea could be applied to gravity.
Right, so he's saying there's this field present for magnetism and electricity, that there's somehow this thing, and there's waves through it, so we vibrate the field. So there's no such thing as a ton, so to speak. There's just a lump in the string. It's a vibration in a string, or a vibration in a medium, and somehow the vibration doesn't spread. It stays where it's going, and all of its energy is retained, so there's no loss of impact. It's frictionless somehow. It stretches infinitely and resists the stretching infinitely, and I mean, I can go through. I'm just saying it's not a very practical thing to talk about, but that's what he's saying. And now he's saying that Einstein's bent space is really just another field. So instead of just electromagnetic, we now have gravitational. So now we can just say the electromagnetic gravitational spectrum, which I think is, and light has to be put on it because now Einstein says light is affected by gravity. So see, it all ends up being the same thing, but in the wrong way. They have it upside down, essentially.
So masses determine a gravitational field everywhere in space.
So let's understand that the real thing gravity is doing when matter exists is that it's creating a shadow. It's absorbing acceleration all the time in all directions, and when something is next to it, it ends up absorbing acceleration in one direction more than the other. So as I move towards something, it responds because I've just consumed acceleration it should have received, and now it doesn't receive that acceleration, so it accelerates towards me. And when it accelerates towards me, it absorbs acceleration I should have received, and now I accelerate towards it. And you can see it's a feedback inductive mechanism where the shadow gets darker and the force gets stronger, and you crash into each other.
Gravitational field exists even in empty space.
Right, so that's perfectly agreeable, but let's understand that I would argue this word field has to be better described. They're not telling us what the field is. It could be strings, it could be blocks, it could be dominoes, it could be marshmallows, it could be tons of things that they stick together and then say vibrate in a special way where no vibration ever spreads, it just goes right straight where it's supposed to go, unless it goes through slits, because then it spreads all over the place and does all kinds of weird shit, but somehow finds the right endpoint. So the field can give waves of electromagnetic force radar if they need it. So if they need radar for a special circumstance, the field will say, here, you can have radar today. Something like that. Where I'm arguing the field is just the energy that exists in the universe in the form of quanta moving the speed of light. So the ones we can't see that have various polarizations, random, and no set frequency between them. They're not on the same vector going at a specific exact distance. Those we call gravity. The ones that do have a frequency, that is, they come at specific distances from each other and are polarized, we call that light, or the electromagnetic spectrum from radio waves to cosmic rays. And lastly, there's magnetism, which is no frequency, but all polarized in one direction.
For example, the Earth sets up a gravitational field in this room. Now that field is nearly uniform. It's about the same everywhere in the room. And it points downward. In fact, that is how we define downwards, the direction that the gravitational field points.
Well, that's how you might do it. I do it because I have an up end and a down end. And so, yes, gravity makes me stand up like a magnet. I have to have the right end sticking up. But it's for different reasons than a magnet. Obviously, my feet aren't more attractive to the ground. They're just that I've been built by evolution to function better this way. But anyway, let's not go into that kind of technicality.
Down means the direction of the gravitational field. So, an object in this room, like this apple, experiences a force due to the local gravitational field.
Right, but let's understand the force it's experiencing, it was experiencing when it was in this bowl, and it was just at a different level. But if I put the apple in empty space, that's when it experiences the most force, because then it's being accelerated in all directions. So obviously it gets accelerated left, it gets accelerated just as much right, which ends up being deceleration of the left acceleration. So they just cancel each other out. And what we're talking about is a lack of equilibrium. So in empty space you have maximum force, but you have perfect equilibrium. And then in complex space, where you're in a field that has other things in it, the other things will create shadows in your field and disturb the equilibrium. You will no longer receive as much acceleration from the places that have more matter, and you will tend, over time, depending on the strength of that shadow, to drift in the direction of that lack of equilibrium, the diminishment of the force.
The falling apple gets its marching orders directly from the field right here.
So let's understand, it gets a ton of marching orders in empty space. It's just that the marching orders are go forward, go back, go forward, go back, go left, go left, go left, right, 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 go left, and it all comes out equal. And all we're doing in a field is changing the equality. So in a sense, again, movement is a demonstration of a lack of energy, not the presence of energy. And the real thing that creates the visibility of energy is the lack of equilibrium. When you break equilibrium, you see the energy that's in the universe all the time. You see a little bit of it. The lack of the imbalance is what you're seeing.
Not directly from the Earth down there. It seems.
Well, yeah, it's not getting the Martian force directly from the Earth, but it's clearly getting the force is clearly changed by the objects. And so it's kind of just silly to talk about everything being local when the cause of that local disturbance is not local.
It's like science fiction to say that the Earth is surrounded by a force field. But that is exactly what gravity is.
Right, says you. So again, it's just this definition of what it's made out of. A dead ether. Well, see, that's what they're trying to say, is they can wave things through it. But if they make it a live ether, then they can explain gravity. So this is how you unify, right? This is why Einstein couldn't unify, is because they were creating fields and not recognizing that there's only one field, and you have to start at the biggest, densest field, and the rest of the other fields are just nuances in that field. So if you don't identify the first field, you obviously can't identify the ones that have feathers in their head, or the ones that have blue eyes, or something like that. If you don't see the fish, you can't see the fish that are different. And so they're seeing the different fish, and they don't realize that they're just fish.
And lots of gravitational physics sounds very natural in this new field language.
Well, yeah, I'm sorry, bent space-time does not feel very natural, so you can say that all you want, but it doesn't feel natural to me at all. It feels like quite a synthetic, strange beast you're trying to massage my butt with.
For instance, here's the principle of equivalence. All objects have the same acceleration in a given gravitational field.
Well, I don't know. I mean, in a given gravitational field, it means you'd have to be in exactly the same location, because the gravity is never totally consistent because of this very random thing, the very idea that it's randomized. And so at any one moment of time, the two spots can have different gravities. But whatever, let's not get into the details.
Here's the tidal effect. The gravitational field can have different values in different places.
Yeah, well, so this is just saying what? The same location in the same location. If you say the same, so that's almost redundant now. So I mean, these aren't very well articulated principles, in my opinion. They're not very useful. But I mean, obviously different locations in the field have to have different values because of the way the force is created. It's always spreading, it's always diverging. It never comes from a non-diverging source, so that diversion, that's got its own word you can use it. That diversion of the force spreading makes it impossible for two locations not to have different causes anyway. They might have the same, they might be compelling a similar vector, but it's always going to be a vector that's converging or diverging. You can't really have them create two parallel vectors in two different places in space. I don't think so.
Here's the idea of hydrostatic equilibrium in field language. At each point in a body at equilibrium, pressure forces balance the local gravitational field.
Hydrostatic equilibrium. At each point in body at equilibrium, pressure forces balance the local gravitational field. It just doesn't. I don't know what is that saying, like if I took two identical planets and I put something in between them, but that would still require the external field to be uncluttered. It's not a solar system or something, or it's not. You'd have to go to some point in space so isolated from any imbalance, and there's not really any such place. Everywhere in space there's some kind of imbalance. So it just doesn't work, I don't think. Yeah, so I'm going to say this doesn't work, I don't think. The universe is going to tend to be a big sphere. It's going to tend to be doing the same thing. It's cause the same effects that happen here are going to happen on that big scale, because there's always going to be fringe, things that are on the outside and things that are on the inside, and things on the left, things on the right. And they're going to move. The things on the right are going to move left, and the things on the left are going to move right, because they're going to sense an imbalance.
So, is this just a different way of speaking, or is there anything really new in it?
Yes, it's just a different way of speaking. I think what you're basically, like I said, the argument is being made. You're basically conceding now where space-time, it really isn't space-time, it's field-time. And once you call it field time, well then you get the time out of there, because now that doesn't become a very fancy concept. The idea of time being a dimension is kind of silly. So we know it's the field dynamic that you're really talking about. And what does the field do? It does carry change. It carries change. It carries imbalance. You can put imbalance into the field. The imbalance can go from here to someplace else, and it does it by certain rules. It travels by the speed of light, and it diverges as it does by the inverse square law. Now I say you can explain all that with a universe made of kinetic BBs, just to and make it simple. You can make your field out of dominoes, or you can make it out of rubber squares, or you can make it out of some other kind of thing, but that's not going to explain gravity then, because then you have to make your rubber squares want to be bigger. You have to create the pressure. And the easiest way to create pressure, especially straight line pressure, is just to make everything move.
Well, I think we can identify several new concepts in the field theory.
Well, I think my new concepts are rational and logical and fit the evidence really well and unify everything and tie it all up in a nice little package, and yours does it.
First, the field exists even in empty space.
Right, but you don't give it any properties. So in empty space you give the field zeros, where it's exactly the opposite. In empty space, uncluttered by matter, the field is its most intense, because all of the energy isn't being blocked by anything that could cause gravity, which is a blocking of force, not the creation of force. Get it? Are people getting it? Yeah, it's really that simple. If you put the energy in the very beginning, then you don't have to explain where it comes from, because it's there in the very beginning. The fish have it. The fish have the energy. The school doesn't have any energy. School of fish moving. No energy. It's the fish. The fish. The fish.
And second, the field is not the same thing as the force that it exerts. The same field...
Ups. Yeah, that's where you... Nope. Yeah, see, we can't agree now. Now we can't just say it's semantics. Okay. So, field is not the same thing as the force that it exerts. It doesn't exert a force. So we're back to the thing again, right? Gravity is not the exertion of force, it's the removal of force. It's creating it's breaking equilibrium by interrupting the field, the force. But yes, the field is the force. The force and the field are all the same thing. It's all force. It's all quanta, okay? And your dead field won't work because it can't create gravity. It can't create gravity. So you're still going to have to somehow make gravity engines. So that's the problem with their theory. They say, okay, there's a field, and somehow when some matter gets in the field, it excites gravity. and now they have to have an engine for it. So now they have to create the divergence and the convergence. So the gravity is basically a convergence. Everything's converging to the center of the material object. And now they have the problem is they made the field converge, but where did it go? How does it get back out into the field again? You know, they don't have a. Then they have to create something silly like Hawking's radiation. You know, we'll just make an anus somewhere, and it somehow, farts it into the end of the universe or something. They have to complete their circle some way, and there's no way to complete it.
There are different forces on different objects placed in the field. The apple and I, here in the same gravitational field, experience different gravitational forces.
Right, but you only do that because of things like your mass, and there's a cause to that effect. It isn't a magical change in the field. It isn't a for no reason cause in the field. Well, I've just explained the reason. The reason is quite obvious. The energy comes from the field, and you block it, which is breaking equilibrium, which causes movement.
Third, objects get their marching orders locally from the field.
They feel everything locally. I mean, it's like saying, I see photons locally. Well, of course I see the photons locally. Of course I see light locally. But clearly, the important facts about the light, what it reveals, exists 50 feet away or 500 million light years away. That's the interesting part of me receiving the energy. I can gain the information about much more than my local field. I can see very distant field circumstances through that mechanism. So to do this local thing is fine. I mean, obviously, the baseball has to hit the bat before the bat can hit a home run. But it's kind of silly to say the baseball didn't come from a pitcher. Come on. Or to imply that we don't need the pitcher.
At their location. Fourth, a field can vary from place to place and can change over time, but it doesn't really move.
Okay, so the field changing from place to place, I don't buy that. I don't think the rules of magnetism or electricity or gravity are changed from place to place that we know of. I'm sure you could go maybe outside the universe and there's no gravity because there's no energy, because there's no quanta or some kind of rule like that, but that's not anything we're familiar with, so I don't see any point in making it an axiom. The change over time says like again, how do you know any fields have changed? So that doesn't really work, but doesn't really move. Again, you're saying the thing going through the field is just a vibration in the field. It's a lump in the field, a bump in the field. The field doesn't have any of its own energy, so how could it possibly move? It's just carrying movement by your description. But clearly, yes, you can't get rid of the randomness in the overall field. All you can change, are the elements like frequency and polarization.
Anyway, the field already exists everywhere, though some places it might have value 0.
So again, that's where obviously there'd be a huge conflict here, because no, there's no place 0 value would be when you've blocked all gravity from all directions. So that might be the center of a black hole or something, if such a thing could exist. But I don't think there's theoretically any place you could do that. And so this is one of those. The exact opposite is the truth. That you might find some place in the universe very distant from any other objects, where the value is 99% of the maximum value. I don't think you could ever get a perfect 10 thing.
Field doesn't move. That means that if mechanics...
Well, let's just understand, movement would be some sort of lack of equilibrium. And obviously the whole field can't have a lack of equilibrium, but certainly the local fields can have tremendous in balances in equilibrium. It's just that whatever's going left in the local field, the overall bigger field has to have some right in it. It's that kind of argument. So if you localize a change, that the trade-off for that change, the equal opposite reaction, will end up in the bigger field, and ultimately in the biggest field it's always going to come out 50-50. So you can't change the 50-50ness of the whole game, but you can create elements or places where the game is 20-70.
This is the science of force and motion. And a field isn't a force. A field doesn't move.
Okay, well, the field is force, and the force does move. Okay, the field of force doesn't move. The force moves. The thing's the fish. So I would say a field is fish, and the fish can move locally. They can move locally, in a sense. You can create the school. Okay, but if you have a school going right, there's a school somewhere going left.
Field is beyond mechanics.
Well, says you. See, that's just another statement. The field is beyond mechanics, so we don't have to apply any of our logical up, down, left, right rules. We don't have to conserve energy. So that's why he's saying this. Field is beyond mechanics. This is just another way of saying we can't create a conservation of energy with this field we created, so we're going to pretend it's not mechanical. It's beyond mechanical. That way we don't have to account for the energy problem. And the irony of this is, if the guy 300 years ago who proposed particle gravity, Lesage gravity in its reformation, Lesage, the guy who stole it from the original guy, but anyway, if he would have said something like, look, this is a field and it's beyond mechanics, see, then nobody could make the argument to him, it's going to create heat, or it's going to create friction. See? He could just say it's beyond mechanics. So this is just a cop-out. And it's a cop-out they use because they're them. Okay, and they won't let somebody else use it because they're them. See? It's like us is okay, we can do it. The us's. But the theys, they can't do this. They're just cheating. Disgustingly cheating.
Faraday said that an object gets its marching orders locally. There is no instantaneous action.
Right, instantaneous would be silly. So yes, so what we found out is that they all move at the speed of light. Yes, coincidentally. Not really a coincidence. All the fish move the speed of light. They're all fish. Get it? All the forces are the same thing. That's why they're moving the same speed.
And at a distance. But isn't that cheating a little bit?
Oh boy, you should say so. Yeah, the whole game you're playing is cheating a lot of bit.
Doesn't the field itself get its marching orders at a distance?
Yes, it does, but by the speed of light. Its information is moved by the speed of light in this universe, and there's no other way to do it.
Not really.
Yes, really.
Let's go back to the electric field. A body with electric charge is surrounded by a field. Faraday visualized this by drawing lines in space.
Right, well, these lines maybe aren't too helpful because it's drawn as in and out, and that's not really what's happening. You know, both are producing an out field. Both are doing the same thing of gravity. It's just they're blocking. One is blocking a certain polarization, one is blocking another polarization, and those are inversely related to each other. So the stuff, the red produces stuff that red hates. Okay, like, you know, red poo. Okay, red doesn't like red poo, and blue doesn't like blue poo, but they really like the opposite. You know. So blue don't like blue poo, but it loves red poo. That kind of thing. Alright, it's all very disgusting, but that's really the game being played here.
Direction of the lines indicates the direction of the field. The density of the lines indicates the strength of the field.
So again, these lines are kind of deceptive because it ends up making it look like the field goes around, but the field is always a straight line force, and these lines are really, these curved lines are really points, and the real vectors that made this are straight lines from these two sources. So two straight lines converge here and create a neutral spot. So these lines represent the neutrals within the where the two balance. The strength of one of the blue attraction is equally compensated by the red repulsion, equally between the two of them. So the force of the negative forces by this one and the positive forces by each one of these have the attractive and a repulsive nature, and so any test charge put at these locations will be neutral. See, in electricity you can use what they call a monopole, but I won't even get into it because it's really not a monopole. But anyway, it's just that the other pole is in the bigger field. As I was saying before, if something's going left, there's something somewhere going right. Well, that's where the other pole is. It went right. It's in the bigger field.
So the charge is surrounded by radial field lines, and that means that the field is radial in direction at any point, and it's strongest closest to the charge where the field lines are bunched together.
Right, but it is all straight line force. So again, those lines just represent the strength, and the position of them is just identifying essentially a neutral. So it's not really a good representation, but you go by how close the lines are together will tell you how strong the force is, because obviously as the force diverges, so obviously the closer lines end up, that means you're closer to a charge by implication. It's the only way to have close lines.
Now, move the charge. Does the field respond instantaneously? Actually, no. The change in the field spreads outward at a finite speed. The field...
Okay, so they just, I don't know why all of a sudden it did this thing, but clearly what they're just indicating here is that there's this is radiating at the speed of light out. So if you make this go incredibly fast, okay, then you'll start bending these field lines because they won't be able to radiate, they won't get very far as this charge moves. And so they, if you can still see this when it's here and the charge is moved here, then you're going to stretch these lines out. But that's not what really happens, because at any one moment these things only exist here for, they're not permanent residents of these locations. So this is almost like, you know, this is like ghosts on a cathode ray tube. It's the old glow is still there, you can see it, but in real time none of that would be visible. None of that would be experienced as any part of the field, because this stuff is moving the speed of light, this stuff is moving this, everything's still moving the speed of light. Nothing's moving any faster or slower.
At one point affects the field at the next point, and so on. It takes some time for news of the change to work its way out to distant places.
Right, and that's the speed of light. This radiates just like gravity. It blocks and repolarizes the field. So this thing, you could say this little plus is taking in stuff coming in all directions, and we could say these are the lines going out. So stuff comes in blue and it goes out red. That's basically how charge works.
To describe this precisely, we need some field equations. These are mathematical relations governing how the field varies in space and time. These field equations are not quite like any of Newton's laws. They do not directly describe how forces affect motion.
Let's understand that the field equation has to account for events happening over time. So as I pointed out before about gravity, it's induced. So that means as I accelerate a little bit towards you, I create a little bit of acceleration in you towards me. And then I sense your acceleration and I accelerate a little bit more. And then you accelerate a little bit more. And then, so that's what the equation is dealing with, is that induction takes time. So that's really complicated, and yeah, I don't know. It's something, first, I don't know if we really need to ever figure that out, but even if you did, yes, it's good to have an equation, but obviously the equation that can do all that summing of timed calculations that change all the values of all the variables, right? All the variables change as we start moving closer and closer to each other, and we start causing more and more acceleration. So yeah, it's complex math, but it's not. What's really happening is very simple. So let's just understand, because the math is complicated doesn't mean what's happening is complicated. It just means when you're doing it over time and trying to tell what happens over the period of an hour, that could require an almost infinite number of calculations to do exactly. And if you want to just do it even get a good guess, it still requires a lot of math.
Field equations are therefore not really part of Newtonian mechanics. So for electric...
Again, I was kind of discounting Newton's mechanics, but I'm just saying obviously he had a field equation. It just didn't include the time variables. He didn't do all those time calculations because he assumed instantaneous action, not slow action.
In magnetic fields, the field equations are Maxwell's equations, first put together by James Clerk Maxwell, the great 19th century Scottish physicist. And Maxwell's equations have a great mathematical symmetry and beauty about them. And inside that mathematics,
I don't know if that's terribly useful rhetoric, but fine.
They contain a secret. Using his equation...
I'm going to spoil his secret. Yes. Yeah, this is... Maxwell, they already had established the speed of some force. And so this ends up being the thing where you realize that light is moving the same speed as magnetism or electricity, the EMF, the field part of electricity, is how electricity is excited. And they all have the same speed. And so this is like the critical mistake, is in assuming that light is like magnetism instead of assuming that magnetism is like light. Yes, maybe, and maybe they're both like gravity, because that's moving at the same speed too. Kind of thing. They just combined, they threw light into the electromagnetic category instead of throwing electromagnetism into a variant of light category, which would have been more helpful. And then they could have migrated those two into gravity.
Maxwell is able to show that changes in electric and magnetic fields move through empty space in the form of waves. That is to say...
Okay, so again, he didn't prove they're in the form of waves, so that's just crap. He found that they move from point A to point B, and the wave part is just totally unnecessary to put in there in the form of waves. They move as a force, period. That's what those lines represent. Like I said, they're all straight lines. Let's not pretend that you get those field lines by drawing straight lines from the two objects to get those field lines. Those field lines represent a point where the two forces balance. Equilibrium is recreated. Well, it's not perfect equilibrium. It means the two forces combine to create a perpendicular launch point. I mean, it's a neutral from which you would have to leave perpendicularly.
As moving, oscillating disturbances in space.
So moving, oscillating disturbances in space. Again, no need for any of that oscillating disturbances in space stuff beyond the fact that, yes, they found that they can transmit this energy into a conductor by alternating, by turning it on and off. But the frequency isn't necessary. It's just necessary to creating, to allowing the field to collapse and then reestablish itself. So if you want to continue to move electrons, you have to let the electrons back in. I mean, it's like blowing water out of a straw. To blow more water out of the straw, you have to let water back in the straw.
Speed of the wave is determined by electric and magnetic physics. So,
speed of the wave is determined by electric and magnetic physics. So it's just an assumption. It's just established by the fact that there's a constant, a speed that the quanta move at, the force moves at. And again, the fact that they all have the same speed should have indicated you go with the simplest thing as the answer, not the most complicated thing as the answer.
Electric force between two charges is governed by an electric constant, something like Newton's constant G for gravity. And we could do an experiment to measure its value.
I don't think it's anything like the constant G for gravity, but go ahead. I mean, the speed of something is a lot more material than the kind of fudgy constant created to make math work, G.
And there's another constant that determines the magnetic force between two wires carrying electric current. And again, we can find that force constant, by means of a laboratory experiment. Maxwell...
So he's just talking about, we measure the speed of magnetism, we measure the speed of electricity in terms of the force being conveyed to some other object. So whether you're converting electricity into magnetism or you're converting magnetism into electricity, there's a speed with which you can do that between two material objects, and that speed is the speed of light. I mean, that's the constant. So he's established that speed, and now we find out, oh, it's the same as the speed of light.
Shows that the speed of his electromagnetic waves depends on these two constants. And from the results of electric and magnetic experiments, he calculates that speed. It's called c, and is equal to 3 times 10 to the 8th meters per second. That's about 300,000 kilometers per second. And Maxwell...
Just a huge number, people. I mean, no one appreciates this, but 300,000 kilometers per second, 180,000 miles a second. It's really, really, really fast.
Realizes that is the speed of light. In Maxwell's day, it is known that light is a kind of wave phenomenon.
There we go. So in Maxwell's day, I say bogus to that argument, and I say they have nothing, there's just no evidence to associate something like frequency and say every time something has a frequency, it's moving as a wave. It's just silly. I mean, if I shoot cannonballs, you get it. Alright, I mean, yeah, I can shoot them at exact time intervals and they'll move through space with a fixed distance between them. And if they hit a drum, they'll make a sound that sounds like it's a wave. The wave certainly will be made. But we know, you know that the cannonballs isn't a wave. It's not vibrating a medium.
And the speed of light has been measured pretty well by that time. What is not known is what sort of wave light is. What is it that's waving?
Well, you said it's this electromagnetic field, but I just think that's a pile of crap that has no magnetic or electric component that you can ever express. And as I've pointed out, what real key difference between a three-dimensional piece of matter and something moving the speed of light is dimensionality. This thing has matter moving in all directions. There's little bits, little quanta, little fish, all heading for the outside surface of this thing all the time. And so it has three dimensions. Light has no dimensions, this way and this way. It only has which way it's going. It only exists in that one dimension. And so, yeah, there's no talk, yeah.
Maxwell says light is an electromagnetic wave, Light is a moving, oscillating disturbance.
Right, let's just understand, light doesn't do anything electromagnetic until it hits an electron. So we know electrons are these charged things. These are we're back to the charged things. The electrons are the things where the force goes in one way and it comes out another color. Okay, force goes in blue, it goes out red. So we know electrons are doing this conversion thing, this filtering thing. Light isn't doing any of this. Light is merely pushing an electron, giving it acceleration. It's a fish going into the school. The school moves a little bit because of the fish's added directionality. And then if the school says, well, we don't like this fish, and they let it go, then it stops accelerating. Okay, it doesn't, and it has to decelerate. In a sense, it'll let a fish go some other direction. So it'll move in some other direction. But the point is, it'll create the fish leaving through that process, through the moving, the actual acceleration process. That's essentially the perpendicular field created by electrons. So that's the electromagnetic component. It's only created by the electron. It's not created by the photon. The photon only adds the energy that the field created will be made out of.
Disturbance of electric and magnetic fields in empty space.
Well, again, so no point in saying empty space. You're saying in the electromagnetic field. So light is a disturbance in the electromagnetic field, not in anything called empty space.
This means that fields are not just complicated ways to talk about forces.
They are incredibly complicated ways to talk about forces, when the simple way to talk about forces is talk about forces. Just talk about what the force is doing. Cause and effect.
Fields are real in themselves.
There we go. Fields are real in themselves. Well, yes, if you understand that the light is traveling through a bunch of gravity, a bunch of quanta. Okay, that the light is only it's only quanta with a label. Polarization, essentially. The only thing really changed is polarization throughout this whole thing. This way versus this way. And if I have a stream of fish and I just change fish at a certain distance to one polarization, then you'll see that as a photon of light. There's still a bunch of other fish in the stream. I just didn't change them to the same polarization, so they have no meaning to what is recognized as the light, which is the distance. It's important. The arrival time is important to the electron's ability to capture the photon. Alright, we're just about out of time, I think. Well, let's see if we can stretch it out.
Physical phenomena of their own, without any particles of matter being present. Because light can...
Again, there aren't particles of matter. It's kind of the wrong verbiage. It's like calling a school of fish a particle. You can do it, but it's not going to make conversation easier. It's going to make it harder.
Carry energy and momentum from place to place. The fields can carry energy and momentum from place to place. And these fields are not really part of mechanics. Mechanics is the science of force and motion.
Well, again, they're not part of mechanics. It's just a cop-out. Yes, the force and motion. Well, again, if you're not understanding the force correctly, again, you think gravity is a positive force, when in fact it's a negative. It's taking force away. It's shielding something from force rather than giving it force. So you're not even identifying those things properly. So of course you don't understand how the field works.
That is, the science of how particles of matter move around. The fields are not made of matter, so they lie outside the realm of Newtonian mechanics.
Well, again, Newtonian mechanics applies to things that are not matter already. Light, for example. Newton did a lot of experiments with light, so I think you're just cheating. You still need cause and effect explanations, and to say you have a gimmick, an explanation that lies outside the rules that have sort of been established, dimensional, yeah, well, that's what all they're doing, right? I mean, we thought there was rules. Yeah, there's 3 dimensions, and all of a sudden they're just going to invent new ones.
Now, this was a hard notion to accept in the 19th century. Maxwell himself tried to think of electromagnetic fields in a mechanical way. He imagined complicated displacements in an all-pervading substance called the ether.
Right, and that would at least make some sense for you just to concede that that's what you're going to have to make your substrate out of, is out of something. So whether you call it an ether or something else, it doesn't matter. But the problem is until you make it move, okay, then you're not going to be able to explain gravity, and you're not going to be able to escape friction. So you've got to make it moving the same speed as all the other little bits, and then you'll understand that fish, when two schools interact, the fish are always moving the same speed. No matter how fast the school is moving, the individual fish are always going the same speed. So every interaction happens at exactly the same speed, because the fish are going the same speed. And the school can't add speed to the fish. The fish add speed to the school. Just understanding that alone. The quanta give atoms their movement. The atom doesn't move the quanta.
And in that case, light waves would be mechanical disturbances, like sound waves in air. In other words, light would be just vibrational waves in the ether. But Maxwell found it hard to make this idea work out in detail. You need to make some pretty amazing assumptions about the ether. First of all, the ether must fill all of space so that the light waves can reach us.
No big problem to do that.
From distant stars. And the ether must have almost no mass at all.
Well, that would be fine too, wouldn't it? I don't understand why these are problems. Like if I was to say the whole universe was made out of rubber marshmallows, Planck size, what's the problem? I'm saying that the only problem I would have is that obviously it's not moving, and so therefore you can't create gravity. But beyond the problem of the gravity problem, what's the problem? I mean, see a problem.
Or we would see its gravitational effects. And finally, the ether must be incredibly stiff. It must be more rigid than diamond, so that the speed of the waves can be so very fast.
Well, again, obviously, if it was carrying a certain frequency, it would have to be conducive to carrying that frequency, but I'm just saying that's obvious. Let's just make the marshmallows smaller, and then they can vibrate faster. So they're very small marshmallows. So that's no problem.
Well, Maxwell himself was sensible enough to separate his mathematical field equations from his speculations about the ether.
I.e., we don't pay any attention to half the shit he said. We just pay attention to the field equations because that's what we chose to do. It doesn't have anything to do with what Maxwell did. I think Maxwell took all of his stuff the same kind of serious. So, yes, you're just pretending that, well, we've decided that part he said was crazy, so we'll just pay attention to the stuff that wasn't.
But suppose he was right. Suppose light really turns out to be a mechanical wave in the ether.
Well, that's what you're saying it is, idiot. I'm sorry, Mr. Idiot. I am Professor Idiot. I mean, isn't this whole fucking thing where you just did all this fucking field crap, aren't you basically calling it a wave, for fuck's sake? You're just saying it's a wave. Well, what's it waving through, jackass? I mean, fuck. I mean, can you get your story straight? How can it be a wave if it's not waving through something? Shit.
Then light would be something like a sound wave. The speed of sound is much slower, of course. It's about 345 meters per second. Roughly a millionth of c, the speed of light.
That's because it's moving molecules, right? And molecules are really big, but the little tiny parts, right? The quantum, the Planck, and all that kind of stuff, those are really small parts. So we just imagine very small bits moving.
So let's think about doing some experiments on sound waves. Suppose a steady wind is blowing past us in the laboratory. What would we see? Well, we'd see the speed of sound is faster downwind.
Right, but that's because the field, okay, for sound is made up of atoms. We know what that mechanical structure is made out of. We know the matrix it's made out of. It's made out of matter. That field that conveys sound isn't one of these vaporous, invisible fields. It's a physical material field. So unlike your fields where you're describing what they can do, this field can be moved. Right, so you're moving the whole field. So you can cheat all over the place here because the whole field moves. Not just stuff in the field, the whole field itself can move. So yeah, that's a problem.
Let's say the sound waves are carried along with the moving air. And the speed of sound would be slower upwind. And the same thing would be true whether the air is moving through our lab or our lab is moving through the air.
Right, so I mean, making the comparison again is kind of illegitimate in the sense that your original electromagnetic field was frozen. It didn't move. So you really can't make comparisons to fields that can move to fields that are frozen. And then say, because of this, this rule applies. It's a bad example. You can't make something go faster than the speed of light. You can't push it faster. You can't move the field and then have the thing in the field moving the speed of light. I can't have a baseball pitcher throw the baseball and then I take a hunk of the field and move it twice as fast. And the baseball goes with it. Light doesn't work that way. Can't move the field.
Now, here on Earth, we are doubtless moving through the ether. The Earth orbits the Sun at about 30 kilometers per second, and the Sun orbits in our galaxy at 200 kilometers per second. So there should be a pretty good ether wind blowing through our lab.
Well, let's understand, 200 kilometers per second compared to 180,000 meters per second, or miles per hour, miles per second. Huge difference. I mean, even though it's fast, it's really slow compared to the speed of light.
And thus, the speed of light should be different in different directions.
Well, again, there's no assumption, because if you were saying that you were releasing a fish, you wouldn't say, I'm pushing the fish. You would say you're releasing the fish. So the fish was already going the speed of light. It can't go any faster. All you're doing is saying, I'm going to release you from gravity. If we release the moon from our gravity, if we could just do that, it wouldn't mean that the moon goes extra fast. It would go exactly the speed it's going now. It would just go in a straight line. And that's all that you're doing when you're creating light, is you're letting something that's already going the speed of light continue its voyage in a straight line. You're just letting it go. You're not giving it speed, you're letting it have its speed. And if you, the matter, happens to be going in the same direction of the vector you let the light go in, doesn't mean that you make it go faster. It just means that that electron has a compensating decrease in value to the relative to the matter. So again, we're back to this argument. The fish swim in one direction longer than they swim in the other up and down directions, which means you'll go this way. If I swim more this way and then I turn and then I only go a little tiny bit back and then I turn, that means I'll keep gaining direction this way. I'll be moving that way. So that's all the electron that releases the photon is doing. It's going from here to here as it releases the photon. So there's no change. Well, it's going from here to here. It's going backwards. But it's always, in a sense, its position is always fixed because it's always going the speed of light. You can never change anything. You can't make something, you can't shoot something off of something going the speed of light faster than the speed of light. You're just letting it go the speed of light. It's time to draw a picture of it, I think. But anyway, good point to quit, because then I can start the next video with even more on that whole why people get confused about this releasing something versus pushing something. You're not going to be pushing light out, you're just releasing it. It's like having the bullets already going, 10,000 miles an hour or whatever in a container, and you just let them out. Sort of, I don't know, there's probably a better analogy. I'll find it maybe. Anyway, until next time.